Welcome to Beerology 101. Today we will talk about beer cans. Enjoy! Cheers!
If you ask someone why they prefer bottled beer over can, you will almost always hear the same answer. Cans make the drink taste metallic. The assumption is that the liquid is sitting right up against raw aluminum. But if your beverage actually touched the raw metal of the can, you wouldn't get a subtle metallic aftertaste. You'd get a violent chemical reaction.
Beer is highly acidic, with a pH generally sitting between 3.8 and 4.5. It is aggressive enough to instantly dissolve the aluminum oxide layer inside the packaging. The moment the acid reaches that layer, the metal begins releasing aluminum ions into the liquid while simultaneously generating hydrogen gas. The human tongue is so perceptive to those metal ions that we can detect them at a concentration of just 0.05 parts per million. That metallic taste you think you're getting from a modern can is a psychological trick. Current engineering ensures the liquid and the metal never actually make contact. Looking at this cross-section, you see a microscopic polymer shield, a BPA non-intent epoxy sprayed and baked onto the interior surface. Zooming in, this liner is only 5 to 12 micrometers thick, roughly a tenth the width of a human hair. That impossibly thin, invisible layer is the sole defense standing between your highly acidic drink and the destruction of the packaging. It keeps metal out of your beer and the beer from eating through the can.
Surviving the chemical properties of the liquid is only half the battle. The can also has to survive the physics of carbonation. A carbonated beverage exerts 80 pounds per square inch of pressure, pushing outward against the walls and domed base. For perspective, a standard car tire operates at roughly 35 psi. You're holding a vessel twice as pressurized as your tires. When brewers first tried canning beer in the 1930s, they used heavy steel, but that intense internal pressure effectively turned those early containers into yeasty hand grenades. They routinely burst during transport and storage. To keep the cans from exploding, manufacturers had to make the steel walls incredibly thick. If those reinforced cans survived the trip home, you couldn't simply pull them open. You had to physically puncture the thick metal using a heavy, dedicated tool known as a church key. Building a container strong enough to hold the pressure meant building a container that was severely difficult for consumers to open on the go. In 1959, an inventor named Ermel Fraze found himself at a family picnic, staring at a cooler of beer. He had forgotten his church key. Desperate for a drink, he was forced to pry open his cans using the chrome bumper of his car. That frustration prompted Fraze to engineer a self-contained opening mechanism. He designed a pre-scored sipping hole and attached a small riveted lever. The aluminum pull tab was born. It was an immediate commercial sensation. By the mid-1960s, nearly 75% of breweries in the United States had adopted Fraze's design, and billions of pull tab cans flooded the global market. But the pull tab had a fatal flaw.
Once removed, the metal ring was discarded entirely. Beaches, parks, and sidewalks were quickly blanketed in razor-sharp aluminum. People routinely sliced their feet on them. Worse, many consumers dropped the loose tab back into the can before drinking, leading to severe medical emergencies when the metal rings were accidentally swallowed. The invention successfully solved the physics of getting into a pressurized container, but it accidentally engineered a massive public safety and environmental disaster.
The solution arrived in 1975, when an engineer named Daniel Kudzik patented a new design called the Stay-On tab. Looking at this diagram of the tab, you can see it actually functions in two distinct stages. When you begin lifting the back of the tab, the central rivet acts as the fulcrum. Your finger provides the effort, and the nose of the tab pushes down directly on the scored metal. It acts as a Class 1 lever to crack the seal and safely release the internal pressure. As you continue pulling back, the mechanics change. The point where the lid attaches to the unbroken score line becomes the new fulcrum. The mechanism shifts into a Class 2 lever, allowing you to effortlessly fold the metal flap down into the liquid. With one fluid motion, this dual lever system gives the consumer easy access. Because the flap remains firmly attached to the lid, it instantly removed billions of sharp metal rings from the environment.
Many people still view the heavy glass bottle as the premium standard for a quality drink, but glass has a glaring vulnerability. It lets in ultraviolet light. When beer is exposed to light, a photocleavage reaction occurs. UV rays penetrate the glass, reacting violently with the alpha acids provided by the hops. This reaction creates a sulfur compound called 3-methyl-2-butene-1-thiol, or MBT. This is exactly the same chemical compound found in a skunk spray. That is why light-exposed beer is literally referred to as skunked. Aluminum sidesteps this chemical reaction entirely. Its total opacity blocks 100% of ultraviolet light, and the mechanically folded double seam connecting the lid to a body blocks 100% of oxygen ingress. This cylinder is a refined pressure vessel, optimized to block the outside environment while providing effortless access. It serves as a functional solution to a century of chemical and physical challenges, the perfect vault for the liquid.
I hope you learned something new. Subscribe for more liquid facts. Cheers!